So we are going to continue where we just last time left, where we had some definitions of how we defined what I should say marginal distributions in marginal distributions psi s or phi I, psi s or phi I, as well as conditional distribution where in the denominator you had this thing. So the point here is we have to further, if we want to further just this further, there can be one or two definitions of conditional expectations also, where conditional expectation of an operator A on S1 conditioned on theta j in S2, which is denoted by expectation of theta j this. So we can write the conditional expectations as well as marginal expectations. They can be written accordingly. So expectation, for example, if we write this conditional expectation can be written as exponential. We can write it as lambda I pi, where you can see this is this 1 by pi 1 by pij sigma of pij lambda I, where pij is this it's the total probability, which is the square of this and this inner product of this and this. So you can write this as 1 by pij can further be written as lambda I. We can have pij, we can write it here in terms of this, and it can be phi I theta I psi of s whole square. So it's basically 1 by pj sigma I phi I theta j psi of s phi I a phi j. So this is the way. So in the same way, this is the conditional expectation. So we can also define the marginal expectation in that sense. In the marginal expectation, more or less, we are the relative sub. We are concentrating on the particular subsystem, which may not necessarily be related with the whole of the system. So in that sense, we have to also see marginal expectation of A on S1 can be given as expectation of A can be pi lambda I, it's ij lambda I pij. So you can have pij can be written as here. So you can write it like phi I theta j psi of s square phi I a phi I. So if we introduce projection operators to get, so we can now do further one thing. We can introduce projection operators. Projection operator is an operator, so it may get the state back. So we can use projection operators on these conditional as well as marginal expectations and see how we can see more degree of what I should say dependence of these quantities chosen from phi I and theta j. Phi I and this phi I and theta j. So if we have operators, if we have operators phi I and theta j, if we have operators phi I if we have operators phi I and theta j, so you can say first we can define marginal expectation as pi lambda I, you can say lambda I pij, and you can further, in presence of pij, you can have this inner product of this phi I theta j psi of s square. It's the square of probability phi I e phi j. Phi I, sorry. Now the question is how can introduce projection on operators. So if we have, for example, if we have let for operators phi I and phi j be projections on phi I in S1 and phi j in S2 respectively, and let I1 and I2 be identity operators in S1 and S2. So now making use of the identity operator, we can have, making use of the identity psi of s, we can have phi I theta j psi of s, phi I theta j. For any complete set of orthonormal states, orthonormal set, we can have. So we can have phi I state. This is another state is theta j. These are two states and operating on psi of s. Now for phi I and theta j, we can just substitute these things here, and at the end you can say if you want to write it as inner product, you can say it's equivalent to psi of s. That linearity condition is there. You can come. This comes as phi of I theta of j psi of s. You can write it as a linear condition. Now again, you can just further write phi I and theta j. So we can write it in terms of, we can further write it as phi k theta L psi of s can be written as phi of k theta of L phi of I theta of j m of n phi of m theta of n psi of s phi of m theta of n. Now again, we can have, you can just have this, you can have complex conjugate of this, and you can see, you can just have the same terms on this side. So you can take it like this. You can write it phi of k theta of L psi of s, or phi of m theta of n psi of s. Now you can have these. This is since they are orthonormal sets, so you can have delta theta m, theta n, jk. So you can have it like this: delta km, delta ln, delta im, and delta jn. So the whole of this we can write it as if it's state. So this and this can be written as Pij, Pij for a joint distribution, for joint distribution, distribution, because it will be inner product k is equal to m, l is equal to n. So you can have this thing. You can have joint distribution. For joint distribution, phi of I, phi of G, psi of S. In the same sense, for the marginal distribution, for so this is for marginal distribution Pij, which is equivalent to this expectation value of phi I theta G psi of S can be written as phi of I theta of I psi of S. So it's phi of I square psi of S. So for marginal distribution, phi of I is independent of set theta I chosen. So in that sense, you can say in case of marginal distribution, the choice of subsystem is not influenced or affected by any part of other subsystem. So in that sense, you can see it. So expectation. So the thing which you can say from this is that the measurement in S2. So initially we had the system S is equal to S1 plus S2. So measurement in S2 can affect measurement in S1 so long as measurement in S1 remains unknown. So thus no measurement in S2 can affect measurement in S1, provided that S1 itself, it's that part of the system which is sort of unknown. The parameters or the variables or random variables, they are unknown. But if the case may be that S1 as a subsystem is known, so then the things become different. And we should then have to turn to conditional distributions or expectations. So now, if we want to introduce this thing, how if two subsystems, if one of them is known, how is it going to relatively see how the relative state function varies vis-a-vis the subsystem which may be known. So that's it. Which has this conditionalities S is equal to S1 plus to S2. So now we have to we'll now go for the relative state systems, relative state function. So that will be our mode. State function. So we have to calculate the relative state function. How can determine relative state? So relative state function, so we have to find in a sense conditional expectation of relative state function in which one of the subsystem is known, so how it's going to affect on the other part of the thing. So if the definition starting is psi of state function, its state psi, it's a relative state psi, so its n is normalization. I, so you can have phi I neta psi of s phi of I, where phi I is any complete orthonormal set in S1 and n is the normalization constant. So the first part of it, the first property of psi neta relative is its uniqueness. So which means the choice of basis of phi I is only, it's not clear, it's apparent. So if you want to choose any other basis, now we can see if there is one basis and how we can relate it with some another basis, and how we'll see such that if we have phi of I is basically in terms of Bik zeta neta. So if you choose another basis to prove this uniqueness in that sense, then this Bik star, Bik should be basically delta Jk. So now here you can see we can see here sigma phi I neta psi of s phi of I is Bij, this is zeta j psi of s is zeta j psi of s So you can say to prove the uniqueness as a condition, you can say this is basically delta jk, delta j n k, or you can say so the second property is the relative state which defines which justifies the name the conditional expectation of all operators in S1. Now you can do the same thing. How can from this how can arrive at joint distribution which includes psi of A as an expectation of psi of theta L A relative, maybe this inner product of psi of theta A relative J A times this operator acting on psi theta relative A relative. Again, you can use this psi in terms of this normalization in this, and you can see here n times sigma I phi I theta j psi of s phi of I a of n phi m theta g psi of s theta phi of m. So for a joint distribution, you can have this and this. So this is n square phi I theta j psi of s is basically phi of m theta of j psi of s lambda m delta I m. So we have at the end, so again it's inner product and it can be 1, it can be n square. So it's this is Pij probability distribution lambda I Pij. From the previous thing we can see. So at this point you can say we can put if it's 1, so we can, if normalization condition is 1, so we can say n square Pij if it's 1, and what I should say, if I so if it's 1, you can say theta 1, so you can say sum n square is 1 by Pj. So from this you can say, if we substitute this in A times relative of psi of theta j relative, so it's 1 by Pj lambda I Pij. So again we are coming back to our starting definition, how we define relative expectations in conditional expectations, but here you have we can see you can see this is for these expectations as a, so we have come out with the conditional expectation of operators given by relative states. So this includes conditional operators of themselves as well as projection operators. So now the another property of another representation of composite systems in terms of orthonormal sets theta j in one subsystem and the another relative subsystem. We can do that exercise also. The thing is that we can have any orthonormal system, and so once we compare one orthogonal system with the another relatively another orthonormal system, it's not necessarily the system may be what I should say, the relative system may be not necessarily orthogonal in that sense. Because the other system may be composed system, which is a superposition of the many states which we are taking into consideration. So the subsystem may not be itself composed of the superposition of various states. So when you are comparing that subsystem, which is composed of superposition of various states, and that subsystem relative to this system, we are trying to find conditional probabilities. It may not be necessarily always orthonormal. That's the point. Because we need to be, for example, it might be quite independent for the choice of the basis, where K not may not necessarily be equivalent to J in that sense. Now we can also go for, this is the conditional expectation. We can also go for the marginal expectation of and do the same thing. We have to find the expectation, the marginal expectation, and do the same exercise and trying to find this inner product where this is one of the operators operating on the state and see how things will come out vis-a-vis the thing. So you can have, if we take this an exercise and do the same for can do the same thing for marginal distribution also. So we can see so there exists in general no state for S1 which correctly gives the marginal expectation of all operators. So this is a final thing, but how we arrive at it is that we can take again the inner product of the thing, this and this, which is basically psi relative theta g for marginal expectation, the inner product, which is the operator. This is this can be written as psi theta k relative theta k. So okay, you leave this exercise, it's there in the book. So you can say, so you can arrive at there is no state for S which generally correctly gives the marginal expectation for the operators. So again, the way previously we invoked the notions of density matrix, which might properly, which describes the marginal part of that distribution in that sense. Not for conditional expectation, the marginal expectation for that distribution. Because the idea of pure states and mixed states, the idea of mixed states which encapsulates this thing here was very helpful in explaining the idea of a dense mixture which is encapsulated in those density matrix. So this mixture may not be pure state, it may be mixed state as compared to pure state. In pure state, rho I is 1, the diagonal elements. So these are the other parts of the states which may be dependent on, for example, rho KL, for example. So if we have, for example, a mixture, so expectation value of the mixture so it's written as so while the expectation value of pure state is A of psi AI phi I AJ phi j can be written as phi I A phi j. So it's not the same, but as if we are taking the mixture of those states, mixture of those weights into consideration. So for if we want to resolve this mixture by a density matrix, which consists of states psi j, which are weighted upon by pj, and working on the basis of this is the pj, working on the basis of orthonormal sets, where psi is given by AGI phi of I. So we can now define a density matrix here, which can be defined as rho KL, can be defined as BJ is here. It's AJ star L, AJK. So we can say where AJ I can be defined as states in product states phi and psi on a given basis. So from this you can say there can be an exercise so we can say the expectation can be written as phi I A phi L. So you can see this entire thing if it's If you want to represent it by as a density matrix, you can say this. You can write it as, ultimately it will come out to be rho Li A I L. So it will be trace of rho of E, which will come out this way. So any in this, from this you can see any this thing can be adequately be represented by a density matrix, and such that it's Hermitian, rho of k L star maybe rho of L k. Now we are coming back for this thing. How we defined subsystems, which was composed of S1 plus S2. And if we choose an orthonormal basis, which is like zeta I and neta j, for these two subsystems S1 and S2 respectively, and if A be an operator, now we have to find the expectation value of expectation value. We can write so expectation value we can write like this. Expectation of A is E of I square psi of S. So we can write it like this. Zeta I neta j So if you do the inner product again, you can just simplify it. You can write it as this Hermitian of this state. So basically we are having two orthonormal bases, this and this, which are basically two subsystems, S1 and S2. And we have to find a expectation vis-a-vis these two. So you can have this can be as a conjugate of this, and you can write it as so I'll not write the next step, so I'll just write the subsequent step. So it will be star will be zeta L neta j psi of S, zeta I A zeta L, or again it's a trace of rho 1A, where rho 1 is defined as the basis of, rho 1 is defined as basis of to be rho 1 L1 is sigma j and in the similar fashion, this is for rho Li. You can have rho Li. Now you can also have rho 2 Mn. So you can have another inner product of another this thing where we have M and N. You can say it's like this: theta I N. So L it's M, theta S. So it's theta zeta I. This is neta since M, zeta S. So in summary, we can say what I should say. In summary, we can say this composite system, which is basically this composite system is basically joint distribution. Composite system is composite system. Composite system is joint distribution. Sorry, composite system leads to joint distributions over subsystems. And so joint distributions can be related with composite, or composite systems lead to joint distributions, but over subsystems, which may or may not be independent, So when they are independent means once we have to define conditional expectations as well as how we can figure out marginal expectations. So for marginal expectations, things can be independent. For conditional expectations, the different relative subsystems are somehow related to each other, or the proper word is, the statistical word is, they are correlated. And we have invoked the notions of density matrix to just see those subsystems, which for the marginal distributions, the density matrix, the next state, it was more, the compositivity was more, for that system, it was more, you can represent it like that. So we cannot ask fundamentally whether there is something called an absolute subsystem. So this is always there is a relation of how relatively different subsystems are relatively related to each other via these conditional expectations. So that's the point. So the notion of the way we cannot talk of absolute entropy of a system, we talk of relative entropies of a system. So it's besides the point that the entropy of the total system may be increasing or constant. So, but if a system is composed of two subsystems, so we can see how how we can relate two or more subsystems vis-a-vis each other in a given formalism. Yes, and we can also calculate conditional expectations as well as marginal distributions in that state. So we'll continue the same, and then we're going to continue it.